Hey, welcome everyone. It's another week for Icon seminar, or Friday Icon seminar. We have, I think, including this, we have 2 more weeks. So the next week will be our last seminar of the semester. And I want to introduce today's speaker, Professor Robert Gregg, is an associate professor at the University of Michigan in the Department of Robotics. It's a new department. It started from it's Institute of Robotics, and then now it becomes a part. Professor Gregg earned his PhD and master's and PhD at our neighboring school, UIUC, back in 2010, I believe. And after that, Professor Gregg started at the Univ as a faculty member to join. And it's quite interesting that how we actually structure this semester, because Professor Spong was the advisor of the Professor Gregg. Now it's quite lovely to have this nice meetings. So I guess during the lunch meetings, I think some of your students ask about, are you going to talk about the DNA? Now you know that Mark Spong is known for DNA, but actually it's well known for the nonlinear control.
Yes.
And so Professor Gregg are many kind of awards, just to mention briefly, NSF Award, and also the Eugene McDermott's Endo Professorship that is currently, and also NIH Director's New Innovator Award, and also the Borrow Welcome Fund Career Award at the Scientific Enterprise. And let's please welcome our speaker. And
Thank you, Patrick, and also to all the great people that I've met with today. It's been a lot of fun. So I'm going to be sharing some work that I've been doing over the past decade or so on enhancing human mobility with Agile prostheses and orthoses. And just a little plug, our department officially started in 2022, though we've had a graduate program for 8 years before that, and now we have an undergrad program too. But yeah, we have masters and PhDs, so think about applying if you're considering grad school further. But yeah, to motivate the talk, so I want to first talk a little bit about challenges faced by individuals with lower limb amputation. And so prosthesis users tend to have difficulty with variable cadence walking, navigating ramps, stairs, due to the fact that conventional prosthetic legs are mechanically passive. Some of them are smart in the sense that they have sensors and microcontrollers that control variable damping, but they can't do positive work. They also can't do active control of motion. And so that results in intact joint compensations to compensate for the lack of muscle contributions for the missing limb. And that tends to increase the risk of osteoarthritis and back pains, these secondary conditions that develop over time. Now, powered or robotic legs have motors that can restore the lost function of the muscles, but they add substantial complexity, right? With sensors and actuators, you have the part in the middle that determines how to map sensory information to motor actions, and that is complicated. And also they're mechanically more complex as well, electromechanically. And in particular, in terms of the control, the traditional approach to controlling these devices is very hierarchical. So at the highest level, there's different possible activities of human locomotion. So walking on a level surface, you can walk slow, medium or fast speeds. The inclination of the surface can change. You could navigate through stairs, and you may have to sit and stand pretty frequently throughout the day. And so I would call these the primary activities of daily life. A truly functional robotic leg should be able to accommodate every single one of these activities. But the traditional approach to controlling these things is to have a distinct controller for each one. And then for each activity mode, assuming you know what it is, you would have some mid-level controller that enacts that mode. But even knowing what mode it is a challenge in itself. So activity recognition or intent recognition methods are inherently challenging. And then once you, but even if you assume that you know what that mode is, then you also need to design a mid-level controller for that mode. And so many of them look like this finite state machine we see here, where you discretize the gate cycle into these discrete phases or events of locomotion. And for each one of these boxes, you have usually an independent control law. Sometimes they have similar structures, but different parameters. Sometimes they're entirely different structures. And then there's switching rules between each one. And so you have this kind of explosion in the parameter space and the complexity of the control design and the parameters involved in each one of these modes and switching rules often are user dependent. And so they need to be calibrated or tuned for every user. And when you add this controller for walking to all the other controllers that you could possibly think of for the different activities, it ends up being hundreds of parameters. And so this really cumbersome tuning problem that makes this technology really not clinically viable, especially with multi-joint prosthetic legs, the knee and the ankle, they're coupled. You know, the knee behavior affects ankle behavior and so forth. And so this is why we actually don't see any powered knee and ankle prosthetic legs on the market today. There doesn't exist a single one. There are powered knees and there are powered ankles. They don't work together. And they're also not commonly used either. They're still very niche products. And then and for any one of these modes, we also have a low-level controller that actually generates the torque, using either a proportional derivative controller for position or an impedance controller, which we'll talk about more later. And so for the past decade or so, my group has been trying to take the field from this discrete representation of human locomotion to a more continuous representation. And so we've done this in kind of two big steps. And so one was to have a continuous representation within a gait cycle. So assuming you know what the activity is, you can continuously represent the user's progress through that gait using a phase variable, which encodes progression or timing through the gait cycle. And that way the leg follows the user's cues, synchronized to the user rather than the other way around if the leg was like time-based, right? You wouldn't want a time-based controller on the leg where the human has to follow the pattern that the leg is enforcing, right? So we want the opposite. So we'll talk about that, but essentially we use the residual thigh angle. So we have an inertial measurement unit that attaches to the top of the knee joint here. And then, that is somewhat rigidly connected to the residual limb where the amputation took place. And so then that essentially gives through the hips of the user, they can control essentially the clock of the system, right? The hip is like the crank through the system. And we've also worked on a continuous sense of representation of activities or tasks, where you can imagine that you could parameterize the space of human activities using multiple dimensions. For example, the walking speed could be a real number. The ground inclination could be a real number. And assuming you know where you are in this multi-dimensional activity space, ideally we would have a way of generating the correct joint pattern for each of these points in this multi-dimensional activity space, allowing continuous adaptation as you change your behavior, right? So this is kind of the high level of what we've been doing, and I'm going to walk through each component of this. So let's start with phase. So the continuous phase variable idea is that we want to parameterize where the human is in the gait cycle over time, but not use time itself, right? So we want to synchronize that to the human's motion. And so ideally, the phase variable would have a linear relationship with time, but that's only true in steady state walking. We have a perfectly periodic gait cycle, but during non-steady locomotion, it wouldn't look like this. It could slow down, it could speed up, that kind of thing. And so how do we do that? So we look at the, like I mentioned earlier, the residual angle of the thigh, which is attached to the, which is driven by the hip, the intact hip of the user. And it turns out that the thigh angle has a sinusoidal trajectory. Okay. And so if we know that we're in the descending region of this sinusoidal trajectory, well, then it looks somewhat monotonic. If you know that you're in the ascending region, it looks somewhat monotonic. And the idea is that as long as you know which region you're in, you can kind of unwrap it, right? And turn it into a mapping to time, right? And so we essentially unwrap the thigh angle and turn it into this linear relationship with time. Okay. But if the person stops, then the phase progression stops. If they walk faster, the phase progression moves faster. If they slow down, it moves slower, right? So it stays synchronized based on the hip motion of the user, which again is acting like a crank to the gait cycle. Okay. And so in terms of implementation, the phase, unfortunately, the thigh angle has these kind of non-monotonic regions, right, where this mapping loses uniqueness and becomes not trustworthy. And so we use brief periods of feed forward control where we try to estimate the rate of progression, and then we use time for brief periods when this signal is not monotonic, right? And that allows us to maintain linearity despite the fact that we have these non-monotonic portions. And then we have the phase variable algorithm has these states that as long as we know which state we're in, we can have the correct mapping to phase. And here we show the phase estimate over different inclinations, ground inclinations, and we see that it has consistency, right? So it's somewhat robust to the environment, the terrain of the user. And so now, assuming that we have a reasonable measurement of the phase of the user, then the question is, how do we use that, right? How do we actually use that for control? And so during the swing phase, we do position control. And the reason for this, so when the prosthetic limb is swinging above the ground, we want to give the user predictable foot positioning, right? We want them to have the ability to predict where the foot's going to be based on their hip motion. And that way they can land the prosthetic foot in the right spot and then trust that the leg would then support their weight as they transition into stance phase, right? And so we use a proportional derivative controller for that. And with the desired trajectory for joint angle would be encoded as a function of phase. Okay. And I'll talk about how we generate these trajectories shortly, but just at a high level, it's a time invariant representation of the desired biological joint trajectory. Okay. So that's the swing phase. During the stance phase, we use impedance control instead of position control. We have used position control in the past for stance phase, and it's worked okay, but it feels more rigid, feels more robotic. And really what feels better is when you have more compliant interaction between the prosthesis, the human, and the ground. And so impedance gives us that, joint impedance. So joint impedance is essentially a relationship between motion and force, right? And so mathematically, one way to express joint impedance is through a virtual stiffness and a virtual damper. And here we encode stiffness as a function of phase, the equilibrium angle of the spring as a function of phase, and the damping gain as a function of phase as well. So these are all phase varying functions that we will generate shortly to again mimic biological biomechanics. Okay, so we're trying to make the leg act like a biological leg through impedance control. So any questions about the high level architecture? And we call this a hybrid kinematic impedance controller. Okay, so it's a hybrid controller. So we do have switching from stance phase to swing phase, and then we have a way of smoothing that out so it's not impulsive or whatever. All right, so this is now how we generate those gait models, whether it's position or impedance. So we collect lots of normative, unimpaired human gait data. And so here, this data set, we collected walking at different gait speeds and ground inclines. And so we essentially densely sampled the range of possible walking speeds and inclines. Actually, turns out that 0.8 meters per second is not slow enough. Many the lower mobility amputee participants in our studies want to walk slower than that, and so now we're adding more data. But initially, we collected down to 0.8. 1.2 meters per second is good enough for the fast speeds, I think, in general. And then so we have all this data, motion capture data, so that includes joint angles, velocities, and ground reaction forces. And then we use that to generate these parametric gait models. Yeah.
You use a healthy specimen, like person who is your intended speaker, right? A healthy person is,
Yes, it's a yeah, unimpaired. Yeah.
If a person is handicapped for that reason, then would they not compensate for that specific handicap and the way they like sort of process the motion system? Because if I'm injured here, I would put more power on the right hand or something.
Yeah. No, it's a good question. So I think my understanding of the question is why healthy data, given that you're working with an impaired population, right?
And wouldn't the data be different for every specific
Well, okay. Well, again, we're working primarily with in this study, we're working with amputees, and so so it's a somewhat homogeneous population, but the idea is that we are trying to restore the normative biomechanics of the missing limb, with the idea that if you do that, if you restore normative biomechanics, they will reduce their gait compensations that they normally have, which are a function of the conventional prosthetic leg not having normative biomechanics, right? So that's a hypothesis. If you restore the normative biomechanics, will gait compensations reduce? And the answer, anecdotally, I can say is yes. It takes time because a lot of these are learned compensations that are hard to unlearn, especially in the span of like one visit in the laboratory, right? But we have looked at this, and people reduce certain compensations very quickly. They don't eliminate them, but they reduce them because, for example, they don't need to worry about ground clearance as much with the prosthetic leg so they don't have to push up with their sound side as much, right? Yeah.
Different the incline.
Uh-huh.
You different the incline of the thing
Yeah.
to test out like different HP and different terrain surfaces. So if you try to collect data that is actually different terrain, for example, like stairs,
Yeah.
or rocky,
Mhm.
that kind of thing.
So yeah, this is just an example, but we will talk about stairs and other activities in a bit. But the more data we have, the better. Yeah. Essentially, they're actually really nice comprehensive data sets now, beyond just this Resnick one that we collected in my lab, that have lots of different activities and different terrains. So yeah, we're still expanding the possibilities. Yeah, we'll talk about stairs soon. All right, so once we have a parametric gait model, the idea is that we estimate gait phase through that phase variable, and then we have ways of estimating the task or the environmental factors that we just mentioned, like ground inclination. And then the parametric gait model, based on those estimates, will generate the desired kinematics and impedance for the leg to follow. So that's the general idea. So here's one of our parametric gait models, specifically for impedance. And so this is only showing the knee and ankle stiffness. So don't forget, there's also damping and equilibrium angle, but just showing one of them. And what you see here is it's a function of stance phase and the ground incline. There's also a walking speed dimension, but I can't show you a 4D plot, okay? So we've, projected down here, but the idea is that the healthy or unimpaired human data helps generate these models. It's actually it's a quadratic program that does it. So we generate these things offline, and those are very efficient. We can throw lots and lots of data at it, and it'll generate these models very efficiently. But it's all done offline. And then once we program the leg with these gait models, then again the idea is we have to estimate gait phase, estimate the task variables, and then we can in real time look up what the biomimetic stiffness, damping, and equilibrium angle is, and then we implement that on the leg. One thing I want to point out is how do we estimate task? Haven't really talked about that, but we use IMUs that are on the prosthetic leg, and so we can imagine if you have an IMU on the foot, you can, if you know when the foot is flat on the ground, you can get orientation of the ground, right? So that's one way to do it. We can also use the IMUs to estimate walking speed and so on, right? We can do dead reckoning for step height, that kind of thing. So we have ways of doing that using onboard sensing. So that's impedance, and then for the swing phase, we have these very similar concepts. They look a little bit different because they're from different papers. But again, we have these multi-dimensional continuous models where we can look up the desired kinematics as the phase and the task change in real time. And then we have this switching architecture. We'll talk about modes shortly. So this demonstrates the continuous task variations in walking, where you can imagine you can program this treadmill to change its walking speed and its ground incline in real time and have the leg measure that. It's slowly changing because that's how it's just the treadmill is pretty slow when it inclines. You can look up here. It is actually declining in this case. So he's walking into a steeper and steeper decline as time goes on. And the leg is continuously measuring the change in ground slope and updating the impedance and impedance parameters during stance and the position trajectories during swing. Okay. And then we also can change speed and so on. So yeah, we can accommodate these continuous variations in real time. And what we're showing here is a comparison between the reference data set. So here's the reference data set that we use to generate the gait model, and then the actual experimental data. And although it's not perfectly matching, we do see the correct trends, right? We see that as incline increases, so the hotter colors are more positive inclines and the greener colors are more negative declines. We do see the correct trend in the joint angles and the moments, the torques of the joints. And importantly, synchronization with the user is important too, because the energetics are very sensitive to correctly synchronizing these kinematics and kinetics. And so what we see when we look at the joint work is we actually see the correct trends compared to biological data. So AB, the red line, corresponds to able-bodied or biological reference data. So we have knee joint work and as a function of incline, ankle joint work as a function of incline, and then total. And then the blue FSMC, that stands for finite state machine controller. So that's just like a reference baseline controller that was representative of the state of the art. And HKIC is our controller. And so what we see is that, if you look at total work, the green HKIC, that's our controller, is following the able-bodied trends more closely, indicating that we are delivering the correct amount of work as the environment changes. And you can also see that the ankle's delivering positive work, the knee's delivering negative work, and that changes with the incline angle. So someone had asked about stairs. And so we also have generated these continuous gait models for stair locomotion at different step heights. Okay, so step heights can vary. They typically have a range. So ADA compliance staircases will have a, you know, an approved range. And so we can accommodate those different step heights using these models, again, trained with reference data from unimpaired individuals. And we've also been able to show that, you know, we are delivering more positive work, which means that the user doesn't have to compensate as much with their sound limb, right? So when climbing stairs with the conventional passive leg, all of the positive work is coming from the sound side. Maybe some from the hip on the amputated side, and that makes it really exhausting, fatiguing to climb stairs. And some people can't even do the natural step over step. They have to do step to step, they kind of like shuffle up the stairs. And so actually one of our participants here couldn't do the natural step over step gait without the powered leg. In terms of sitting and standing, there's variations in the chair height, right? And also you can be going up or you can be going down, right? And so we again use it since there's no swing phase during sit to stand, it's only stance phase. We only use an impedance model. It turns out that we don't need different dimensions to accommodate the different chair heights because the phase variable handles that. The phase variable encodes progression, right? And so you can imagine you just progress further into the descent for a lower chair, or you progress not as far for a higher chair, right? So the phase variable naturally encodes different chair heights. We did have to have a different equilibrium angle for going up versus down to have it be more natural. But anyway, that's a longer story that I don't really need to tell. And so you can see here demonstration of different chair heights, which again, with a conventional leg, all that positive work would be coming from the intact joints. And if you look at outcomes, so this is loading asymmetry, which is a common issue. You can imagine if all the positive work is coming from my sound side, then I'm going to be overusing the sound side, right? I'm going to really be loading that and not the prosthetic side. And so what we see here is the solid dots are with a powered prosthesis, and the empty dots are with a passive prosthesis, a conventional prosthesis. And you want it to be around zero, so zero asymmetry between the two sides. And so you can see, you know, especially in stand to sit, you have better symmetry with the powered device. Sit to stand isn't as compelling, but it's still a significant difference. So you can see that they're, you know, they're still favoring the biological leg, the sound side, with the powered device and sit to stand, but it's closer to no asymmetry. And then we also have shown improvements in time trials. This is called a 5-time sit to stand test. We tell them do 5 sit stands in as short amount of time as possible. And this is definitely a challenging thing when all of the work is coming from one side of the body, right? And so we were able to show a significant reduction in the time with the powered device, which is actually helping with propulsion. And so in summary, what we've done is we started with lots of activity modes representing the activities of daily life. Traditionally, there are different controllers defined for every single one of these, and then there's nothing in between, traditionally, right? Traditionally, there are no continuous variations of these things. It's just like one up slope, one down slope, one upstairs, one downstairs. What we've done is we've reduced the number of activity modes and enabled more continuous flexibility. So we essentially unified walking across speeds and inclines under one activity mode by providing more adaptability into the mid-level controller. And then we unified sit-stand under one activity mode, so it can do up and down, and it can do variable chair heights. And for stairs, technically it's the same gait model for ascent and descent. It's all one gait model, but we need to separate them in terms of classification because you need to be able to anticipate whether you're stepping on a, upstairs or downstairs. You can't wait until you hit the ground. You need to be able to, so essentially in terms of classification of the activities, intent recognition, we have to have these things be separate because you have to anticipate whether you're about to hit it upstairs or downstairs. But we can also accommodate variations in the stair incline or step height. So we've simplified the higher level architecture, which then leads to classification or intent recognition. So it is much, much easier to do classification between 4 modes than it is to do however many we had before, right? Much easier. And so the traditional approach with all these different activity modes is to use, machine learning approaches that really they can't get any better than about 95% accuracy. So it's like 5 misclassifications every 100 steps. It's a lot, right? By reducing the classification space to four states, and by using perception, so this is an ultrasonic sensor that allows us to detect the distance to the nearest object in front of you. So we can see a staircase as you're approaching it. This allows us to get about 99% accuracy. This is 2 participants in particular. We've added more participants, and they have similar results. And I'll talk about these results more in a second. But essentially, these are simple heuristic rules that are used for these transitions. It's not machine learning. It's just simple rules that we can explain to the user. They're intuitive, they're interpretable, and if they make a mistake, we can explain what went wrong, and then they can learn from that, and then make fewer mistakes in the future, right? That's how we were able to get closer to 99% accuracy, and then we have a 100% recovery rate because once they recognize there's a mistake, they know what to do to correct it. Okay. And so here's some results. We had both a self-paced and a rapid pace condition. So looking at the self-paced condition, we had both intact leading and prosthetic leading transitions, which is also a somewhat unique feature, is that a lot of existing classifiers require you to lead with one leg. In our case, we can lead with either leg. And so you can see that most of the errors happen during the transitions, which makes sense, but overall it's pretty accurate. And then we also had a rapid pace experiment where we told them to go as fast. They had to walk quickly, and so they were rushed. They didn't have time to think about every single step, right? And it turns out that as time went on, they got better. They get into the groove, and even though there's a time pressure, they're able to still consistently use this intuitive classifier. And you can see there's a ramp too, so they're able to, the leg is automatically adapting to the ramp. And you can see here that one of the participants did 3,000 walking steps. Yeah. So that was essentially like a 5K. Yeah. And then I already mentioned the recovery rate was 100%. But we have, because it's heuristic based, there's backup logic. So let's say we misclassify an early transition to the stairs. Well, then as they begin to get through the swing phase, the gait behavior looks different enough where you can figure out, oh, we made a mistake. So there's backup logic to that. So that helps with recovery. And then we also have ways to manually reset things so they can abduct their hips, and that will reset it as well. So, yeah.
Frequency with which it's updating or doing the classification.
Yeah, so it's based on gait events. So there's so like maximum hip flexion or heel strike or toe off. There's features at certain events that we look at. Yeah, so it's but the rules are super simple, so there's no essentially delay. Once you know the event has happened, then you can look at the rules. Yeah.
What's the distance, Bobby, on the sensor? How far I can see?
That's a great question. It's not super far, but it's far enough to we do look for a pattern of distance reducing. Because we don't want to have a situation where you have like a false positive, right? Yeah, right, exactly, right. So we look for, I think, at least maybe 2 or 3 steps where we see this distance getting smaller. And then that indicates that you are actually approaching an object.
Do you use this to kick a soccer ball?
We do have that, yeah. I don't know if I have it in these slides, but I can show you. Yeah. We've done that. Yeah. All right, so we're trying to expand our impact by open sourcing a lot of this work. So there's something called the open source leg, which is directed by my colleague Elliot Rouse. And so we've deployed the sit to stand and walking controllers on opensourceleg.com. So anyone who has a prosthetic leg that wants to implement these things can just download that code and do it. And we've also been transferring this to the Oster Powerty. So we are currently investigating various endurance and symmetric symmetry outcomes with this device. But just a little preview here, you can see that it's the exact same controller running on this device, except there's no ankle. It's a carbon fiber ankle foot mechanism. So there's just the knee controller, but you can see that it works very similarly. And it's much nicer hardware. Yeah. And you see, he's able to hold, you see what he kicks back the leg, and he's able to hold it back while he's opening the door. That's because the phase variable is seeing that progression has stopped, right? Hold it in position. And then we can do things like kneeling as well. All right, so that's on the prosthetic stuff. Any questions about that before I move on to exos? Yeah.
Is the unit weighted similarly to a flesh and blood leg?
So the goal actually is to make it lighter.
Right.
Yeah, because it's attached to soft tissue, right? And so rather than bone. So it's actually lighter than a biological leg.
Gotcha.
Yeah. Yeah. So the goal is to make it as light as possible.
Related to, and it looks like a couple of the subjects, they're like almost dragging their leg.
Yeah. It's because it's heavy. Yeah. Well, sorry, when I say it's heavy, I'm referring to. Hello. I'm referring to this leg.
Yeah.
This leg is like 11 pounds. This leg is 6 pounds. Less than that, actually. I think it's like 2.6 or 2.7 kilograms. Yeah.
How much is like a flesh and blood leg?
I mean, it's gonna be similar to that one.
Gotcha.
Yeah.
Okay.
Yeah. Yes.
I figured we were comparing like the kind of work for the data between the able body and the HPIC. I'm just curious, but it seems like it's much better for the equal than the weight. Is that just because of the geometry or the weight?
Yeah, that's a good question. Honestly, I don't have a great answer. Yeah, I'd have to look into the data a little bit more. The knee is primarily a damper during level walking. During stair ascent, it's different, but during level walking, the knee is primarily a damper. And so it's possible that the timing or the magnitude of damping is slightly off. And maybe just coincidentally, it was more correct for the ankle. That's certainly a possibility. Yeah. Yeah. Mm-hmm. Yeah.
How do you reckon the availability of maybe of command data will change some of your design? If you had the ability to know advanced, like you wanted to manage that.
Yeah.
Would you like, because you have an IM now to sense that the timing of a certain elevation, right? If you had the ability to know the advice.
In advance. Yeah, so that's what the ultrasonic sensor tells us, and that helps with transition strides. So like transitioning early enough before you hit the environment, right? So that anticipation is really, really important for transition between activity modes. We are thinking about ways to like use perception to know that, for example, the step height in advance before you contact the ground. That could be helpful. Right now, we are purely reacting to step height. But anticipating some of those environmental features could be useful, because then we can have the correct behavior during swing phase before you hit the environment. Yeah.
Are there any like secondary safety measure? For example, the human can have a clicker.
Oh, yeah.
Making the decision at the same time as the sensor. Like what if, for example, the sensor could kick in if the human forgets or is carrying something. Other times humans are better at perception anyway.
Yeah.
They can make better decisions. So they can click, oh, upstairs.
So that's definitely an option. I think they would definitely prefer not to have to manually do things, but stay tuned. We have a smartwatch. Stay tuned. Yeah.
Did you think at all about like enclosed spaces? Cause I know like with
Yeah.
ultrasound, like.
Yeah.
Walking in like a tight space.
Yeah.
The leg's always thinking like you're approaching a safe.
Right. And it's like, if you imagine if you're climbing a staircase and you have to turn and turn around, you don't have those 3 steps. That's an issue for us. But we have the backup logic helps with that. So essentially, the leg won't initially know there's stairs there, but as you lift up the thigh high enough, that is distinct enough from walking that we say, oh, okay, this is now stairs. And so but it's not a continuous thing, right? It's more, you gotta do this first, and then it recognizes it, and then it switches. But then again, turning the corner in the staircase isn't necessarily continuous anyway, so, yeah.
How much accounting do you have to do for variation between people? Like, will the controller be able to make that on its own, or?
Yeah, at the moment, we don't change anything between people, which, it works for everyone, but maybe not optimally, right? So one thing that we're interested in is maybe using reinforcement learning to improve symmetry, which would help individualize things. I have a student working on that. I can't declare that we've had success yet, but at the moment, it's the leg works like the average biological limb rather than your biological limb, but it's good enough to get them moving. Yeah.
Sort of a follow-up on that. Do you think you could give the person like a knob that they can tune based on what they feel is comfortable? Because I've seen like Professor Elliott Brown's like have.
The preference-based stuff.
Yeah.
So we do have some things like that. Like we can increase or decrease early stance knee flexion, for example. So we do have we have a way to do that. But there are so many features you could imagine tuning that if you give people control over everything, the parameter space is enormous, right? And so we're trying to figure out what are the most important knobs. Yeah. So, but as a starting point, we're trying to say no tuning, see how far we can get with that, and then figure out what those most important features are. Yeah.
Very cool.
Yeah.
So in the same vein, first of all, thanks, great job. In the same vein, it'd be cool to do some learning, right? Like my body is, as I descend, pun intended, into middle age, my body is adapting as I go, right? Like I tweak my knee a little bit and then my other leg does more work, right?
Yeah.
And so like, it would be interesting if the prosthetic could sense, oh, Phil's left ankle is tired today. Like, let's change how much support we give with the prosthetic.
Right. Yeah. I mean, I think reinforcement learning could potentially help with that. You just have to do it very carefully because you don't want to do something wrong because it's safety critical, right?
Yeah, you have to have some.
Yeah, exactly. Yeah. I do have more slides if you all want to see them. I don't know how much time we have, but
It's 3:48.
Okay.
But I think you can go with the slides.
okay, yes. All right, we'll see how far I get. It's okay. I appreciate the great questions. So we also are working on partial assistive exoskeletons. So, these are not devices meant for people with like complete spinal cord injuries. These are meant for people that have some voluntary control. maybe it's weakened. But you know, they're able to control their limb kinematics to some degree. And then the idea is we want to offset either weakness or neurological, you know, motor deficits or fatigue in the case of unimpaired, like warehouse workers and so on. And so the numbers in terms of impact here are quite substantial. And so working with partial assistance exoskeletons, they have to be extremely back drivable, meaning that the human joint can drive the motor, because we want the human to be in control of their limb kinematics, right? And the motor only provides torque assistance, right, when needed. And so we also need to be lightweight and generalizable to different joints and so on. And so we have something called the M-Blue, which, you know, Michigan, right, is blue and amazing blue, but it's modular, meaning modular for different joints. And it's back drivable because it has a quasi direct drive actuator. So it has a 9-to-1 gear reduction, very small inertia. So it's easy to back drive. And it provides 15 to 30% of the human joint torque, depending on which joint and how heavy the person is and what activity you're doing. And so that helps with unloading, you know, human muscles. And these are aftermarket modifications to commercial braces. So they're simple to work with, and we simply replace the commercial brace joint with an actuator, essentially. And so even with a back drivable device, you still need a effective controller. It needs to be versatile or task adaptive. It needs to be predictable, safe. It needs to be, again, generalizable to different use cases, and needs to be effective at something, right? Reducing effort or improving performance or mitigating deficits. And so the control approach that we've embraced is an energetic paradigm. So we don't want to enforce trajectories because that would inhibit voluntary motion, right? We want the human limb to be determining the trajectories. So instead, we want to augment energetics in a beneficial way. And in particular, to ensure safety, we're doing energetically passive control. So the idea is that we use the actuators to essentially modify the dynamics of the human and the exoskeleton in closed loop. So you can imagine like offloading gravity or offloading inertia would make it easier to resist gravity or to accelerate, decelerate the body, right? And examples go beyond gravity compensation and inertial compensation. You could also use virtual springs, virtual dampers, and this is all energetically passive, meaning that the human is in control of energy injection, not the exoskeleton, right? The exoskeleton still can do positive work through hybrid dynamics. So you can imagine, like if you had a virtual spring, if you change the set point between stance phase and swing phase, that can inject energy, but it's locally passive, right? And so we have several different components that we put into what we call an energy shaping basis. And then we use, again, human data, multi-activity human data, to optimize over the basis to predict normative joint torques, given the normative input kinematics and ground reaction forces. And so we see here is for the ankle and for the knee, over different activities like level walking, sit stand, stairs, ramps. We see the exo in blue trying to fit the human torque in red across different activities. And it's a single nonlinear equation that's doing this. So essentially, the input kinematics and ground reaction forces are distinct enough between activities that a single mapping can give the distinct torques that are needed across these activities. So there's no classification here. There's no explicit task detection. It's all end-to-end, going from kinematics to torque. And so just to show you, this is modular in the sense that we can deploy this in different joints, whether it's unilateral or bilateral. And I think I'm running out of time, so I'm not gonna go into great detail here. But just, I want to point out that we've also used this for reducing the contributions to quadriceps fatigue during multi-terrain lifting, lowering, and carrying. And we've been able to show that we can mitigate the effects of fatigue during lifting and lowering, which the idea is that we want to prevent injurious compensations, like, lifting with your back instead of with your knees. That tends to cause workplace injuries when people fatigue, specifically their quadriceps. So if we can prevent that fatigue or mitigate the effects of fatigue, we might be able to prevent workplace injuries. So I'm going to skip through the results there, but you can see it in our science robotics paper. But I want to end with a couple quick case studies. This is with an elderly individual who has age-related weakness, and he is unable to do the step over step gait. And so you can see it's kind of like shuffling from step to step, right? And then when we put the knee exoskeleton on him, this is his first try.
Oh, wow. Okay, great. That's amazing. All right, cool. That is absolutely amazing. Awesome, all right.
Yeah, so he was very enthusiastic. And we've also tested it with post-polio syndrome as well, trying to improve, again, sit to stand performance. Similar with the amputee case study we saw earlier. And then multiple sclerosis as well. So this is an interesting demonstration where the device is active right now. Not a bad gait. Obviously, there's a walker there. But we'll turn off the exoskeleton in a second here, and you'll see a big difference.
Tell the person you were gonna do that.
We did. We warned them. You can see he's suddenly dragging his foot. And so there's a acute change between with the device assisting and with it not assisting. And so we're actively pursuing different patient populations now, including osteoarthritis as well. Turns out these devices are pretty, our initial data shows that they're pretty effective at reducing joint pain because they can reduce loading caused by the muscles. So that's an ongoing case study. But yeah, for now, I just want to say thank you for your time, and I'm happy to answer any more questions.
I have about, I think, 10 to 15 minutes for the questions.
Thank you for the talk. So when you do the impedance control, do you consider regulating the contact force within the friction point?
We don't. It's a good question though. Yeah, we haven't had any issues with like slipping. But maybe that's because we haven't yet tried things like walking on slippery surfaces, right? So I do think that's something that we could definitely consider. Maybe once we do more outdoor testing, right? Thank you. Yeah.
Just about you collect a lot of human data and have the there.
Yeah.
And you only plot out the surface area, and suppose it is a mean surface, right?
It is a what?
It's an average.
Yeah,
surface.
yeah.
I'm curious about if there maybe the variation across that surface will be a help or information.
Well, so we do have variation, like we generate a gait model for every individual in the data set, and then we average them together. That helps because turns out that these impedance solutions are not unique. And so having lots of variability in the data helps find I think a better solution. Maybe more representative of biological impedance, maybe. I can't say that confidently. But yeah, at the moment, we are definitely in the end implementing an average model. Yeah. But it turns out that it works decently for most people.
Yeah. Like, so it's like because humans can somehow adapt to that.
Yes.
So average model.
Yeah. But so it's not necessarily optimal
Yeah.
for any individual. but it is functional.
Curious if you thought about kind of like how my other does it with their robotic arms. Have you also thought about looking into the electrical signals from muscles? EEG sensors, because that's what they use like for people kind of part of the drugs or drugs that use for going in the upper body. So if they have their arms read the muscle signals.
Yeah.
And like,
Yeah.
like how you identify the motion by just looking at it.
Mhm.
So I consider that.
There definitely are people in my field who are using EMG signal sources. I am not, just because there's some practical limitations to that. You know, you have to place the electrode and then you've put it in a slightly different location. The signal's different and stuff like that, right? So it requires calibration, right? So I've been trying to see how far we can get with just autonomous feedback control theory, right? But I'm not trying to say though that it wouldn't be valuable. You know, for example, I think that EMG could be helpful for, again, anticipating changes in behavior, right? But it is a noisy signal, right? So I wouldn't use it for direct control of a leg. You can do that with an arm and a hand, because you have the luxury of trying a few times, right? But with a leg, you can't let the leg collapse, right?
I'm curious with the, you showed the outdoor walking with the prosthesis. Have you at all thought or seen, like, are there things you can learn from the person as they are adapting to essentially this, you know, artificial creature you have strapped to their leg, right? Like it has its own like thoughts and desires, as it seems different like sensor feedback. Have you like thought to like look at the human's adaptation to that over time to learn different behaviors that you can put in, or like what compensations people are making, sort of like I swing my hip backwards so that it doesn't, you know, kick the door when it gets
Yeah. Well, we've looked at, you know, like the opening the door. We've also looked at crossing obstacles.
Yeah.
You could also use that same feature to like pause the leg and swing phase and then rotate over an obstacle. So we've looked at that. We haven't done any deep analysis though of over how behavior changes over time, besides in like fatiguing trials, right? We have studied that, like the long distance experiment with the classification study. We see that actually the performance tends to improve over time. So that's what we've looked at so far, but there's a lot more to do in terms of how people adapt or accommodate these devices into their actual, you know, daily use. I think with the Power Knee, we're getting closer to take-home trials. We're getting much closer to that. With our in-house hardware, no way. That hardware breaks all the time.
Follow-up on that question. You're actually using feedback from the participants for changing and tuning any parameter. Is that actually valuable to making your feedback from the participants?
Oh, definitely, yeah. And in fact, one of the individuals you saw with the Power Knee is one of my own PhD students, and he's amazing because he not only understands the clinical side as an end user, but then can also fix things as an engineer. So suddenly our iteration loop has rapidly accelerated. But yes, we certainly take feedback, make adjustments, like, you know, that we still sometimes hear people say, oh, then the knee feels squishy, right? That means we need to increase its stiffness, right? So we do hear things like that, and we do respond to that by updating the gait models. Or I did mention that we have ways to tune these things, but we try in most of the studies I've done so far, we try to hide those tunable parameters just to see how far we can get with the plug and play controller, right? But yes, like there are features that people ask for, like, oh, this is too much early stance knee flexion. I don't like that feeling. Because with a conventional prosthetic leg, if the knee starts flexing as you load it, they're going down. So they want to lock that knee on a conventional prosthetic leg. But on a biological leg, your knee does flex to help absorb body weight, right? It makes it a smoother, more comfortable gait, less impulsive. So our controller tries to encourage that, but some people really don't like it. And so we can turn that off. Yeah. Mhm.
So comparing the C to stand and stand to C, it seems that one of them is more symmetric than the other one. Well, why is that? Just curious about.
Yeah,
physics or,
so, okay, so I have one, I may have a couple reasons. One is that, with that study, I think that was with our in-house hardware. It has an actuator that's probably this big. And I don't know if you noticed, but it was kind of sticking out. So if we go back. I don't know if I can go back, zoom, I'll try to go back. So what I'm trying to say is the knee center is not aligned with the sound leg's knee center. That's what I'm trying to say. And so that causes some asymmetry just between the two legs. So here, you see that, how the robotic leg is kind of sticking further out. And so that makes it hard to properly load it. And so that's definitely responsible for some of that asymmetry. And some of it is just maybe, again, it takes time to unlearn compensations. They're so used to loading one side. And even though this participant has been using our prototype for, a couple of years now, it's not every day. And so they don't necessarily trust it as much, We do have a training protocol though that involves that this is on a force plate, and we can show them on a screen loading levels, and we try to train them to have symmetric loading. But with both their take-home leg and with the powered leg, but then we turn off the biofeedback for the actual assessment. Yeah.
So the important thing we're helping with the improving the symmetry is often part of perhaps the kind of mechanism design.
Well, yeah, definitely. You definitely want the knee sensors to be aligned. Otherwise, you're gonna have, you can just imagine there's gonna be a transverse plane moment between them, right? So, yeah, so this is a challenge with a big actuator. Yeah.
Have you taken the arms movement into account? Because arm can either assist or maybe predict the leg movement ahead. I'm not. Sure
Yeah.
Leg follows arm or arm follows leg, but in running or speed walking competitions, arms often play a really big role in this. But I don't see sensors on the arm.
Right.
I wonder if it could help.
I think extra sensors on the body could help. One of my goals though is to have a self-contained device with no extra sensors, because the patients don't want to wear a bunch of sensors on their body, right?
Right.
So the goal is to see how far you can get with just a self-contained device. But I'm certainly not denying that sensors on like the intact side or on the arms, they could be very valuable, but would people use them?
Smartwatch.
The smartwatch. There you go. I told you, stay tuned. We have a smartwatch project.
I think that there's differences in strength of a muscle between the eccentric and concentric
mhm.
phase. So that might also contribute to the asymmetries.
Yeah, for sure. Yep.
So I also noticed that asymmetric, when you show the different incline,
Yeah.
you have a straight line and different data points. So on the positive incline, the data points are more closer
Yeah.
to the straight line than the next.
You talking about the joint work plot?
Yeah,
Yeah. This one?
Yeah.
You're right. Yeah. So, yeah, maybe that we're hitting our targets better for some terrains than others. Yeah.
I have many questions, but just ask a few because
Yeah.
You mentioned that when stair up turns stair down, the transition period has accumulated there. Is that because the motion was yaw with your IMU, yaw predictions?
Sorry, did I say that you have accumulated error? I don't remember.
Maybe not accumulated.
Yeah.
The transition is where the error actually happens.
Oh, okay. I think what I was trying to say, like if you're in a staircase and you're turning from one set of stairs to the next, the ultrasonic sensor won't see a pattern over time of a decreasing distance. So the ultrasonic sensor won't help us anticipate the object necessarily, at least with our current logic. But what we do have is though, when you lift up your leg enough, the IMU will tell us that, okay, you have a lot of hip flexion, and that is indicative of stair climbing, not walking.
Yeah.
And so we would get that transition during late swing instead of the beginning of the stride. Yeah.
Because my question is on the IMU side, because you basically didn't projective model on a plane to measure the 1 degree.
I see, yeah, yeah,
Think
yeah,
about you're trying to do the dancing.
Yeah.
Y'all terms, in that
Right.
case, I knew not gonna be.
yeah, so that depends on like which axes are intrinsic versus
Exactly.
extrinsic.
Yeah, exactly.
Yeah, so, but we have a pretty good way with the way we've set up our IMU.
I see.
We've got a pretty good like planar measurement that is somewhat invariant to the heading.
Oh,
So, yeah, we thought a lot about this. We do have maybe some sensitivity to like, if they have, maybe, abnormal circumduction or something like that, and that might mess a little bit with our sagittal plane, because then you have like your
Yes.
coupling things. But, it's not enough to like really upend the entire system.
My last question is, can you tell some of the advice to students who actually wanted to study this biomedical application?
Yeah.
Control perspective.
Yeah. Working in interdisciplinary teams is really the key, right? So no one person in my lab, including myself, can do all this by themselves, right? So we have mechanical engineers, electrical engineers, biomedical, robotics, right? So that's all represented in this work. And so, working in teams with people with complementary expertise and like trusting that expertise, has worked well for my group, for me personally. And I do think that spending time with the clinical population also is very important too. So I spent 3 years working at a hospital, during my postdoc to learn the clinical side. Otherwise, I don't think I would have as much of an appreciation for the real challenges faced by the patient population. So spending time with the clinical population is important too. It's not usually good to just assume what the problem is and make a solution in it, because you might end up making a solution for a problem that doesn't exist, right? So I do think that actually having real face time with the clinical population is important too.
Let's thank the speaker.
Yeah, sure.
One of your favorite slides.
One of my favorite slides. Okay, let's see.
Maybe all we can do. All right, what piece of?
I don't know. I think I must have turned on. Okay, I think my favorite slide will be